When we think about the cloud, we usually picture something entirely weightless, right? We imagine invisible data just floating seamlessly through the air. But behind that digital illusion, there's an incredibly heavy physical reality. Consider this. Back in 2017, the original transformer model, which is basically the architectural foundation for modern artificial intelligence, took an estimated 4,500 watts of power to train. Fast forward to the summer of 2024, training a frontier model like Llama 3.1 required a staggering 25.3 million watts. That is literally enough electricity to power a small town just to teach a computer how to speak. The power required to train these massive models is essentially doubling every single year. So the biggest question right now isn't just how smart AI can get, but how on earth we are actually going to power it. Welcome to this explainer for Future Systems Explained. Today, we're diving into the core mystery of the modern digital age: how we're going to fuel the massive physical reality behind artificial intelligence. Because what looks like a software revolution on our screens is actually triggering one of the greatest industrial and energy challenges of our time. You see, for a long time, the tech industry operated under this assumption that the future of AI would be decided strictly by code, by more advanced algorithms, or maybe just more sophisticated silicon chips. But we're reaching a really fascinating pivot point. AI is currently constrained not just by intelligence, but by physical electricity and heavy infrastructure. The next major breakthrough in artificial intelligence might actually depend a lot less on a team of software engineers and a lot more on the construction of a new power plant. So here's our roadmap for unpacking this physical layer of the internet. We'll start with the hidden power problem, map out the invisible AI system, and explore the need for firm power. From there, we'll dive into the nuclear conversation, examine the physical bottlenecks, and finally, map out the future energy portfolio. Let's jump right into Section 1, the hidden power problem. To understand why tech giants are suddenly talking about nuclear reactors, we first have to grasp the staggering scale of global energy demand driven by the rise of generative AI. The sheer scale of the projections we're looking at is pretty mind-blowing. The International Energy Agency projects that global data center electricity consumption could hit 945 terawatt-hours by 2030. That is essentially doubling today's levels in just a few short years. And this unprecedented spike is happening because AI doesn't just store information, it requires massive clusters of servers working intensely to both train the models and run inference, which is what happens every single time you ask an AI a question. All of those machines require massive amounts of continuous power and cooling equipment. Moving on to Section 2, the invisible AI system. AI isn't just a server sitting in a vacuum somewhere, it is deeply intertwined with our regional power grids. The crucial thing to understand here is that data center electricity demand is a local problem just as much as a global one. The infrastructure for AI is highly concentrated. Over 90% of projected compute capacity is located in just 3 regions: North America, Western Europe, and the Asia Pacific. Because these massive data hubs are built so close together, they create intense, localized grid vulnerabilities long before the national totals look extreme. According to recent research, dense regions like Oregon, Virginia, and Ireland are experiencing a power stress index exceeding 0.25, which indicates significant vulnerability. The power grid in these specific areas is quite literally feeling the weight of the cloud. That brings us to Section 3, the need for firm power. This localized stress highlights a harsh operational reality of these massive server hubs, which is that data centers simply do not sleep. Now, this leads to a fascinating question, and one you've probably already thought about. If major tech companies have carbon-neutral goals and AI needs an abundance of clean energy, why not just build massive fields of solar panels and wind turbines? These are the exact companies that have championed weather-dependent renewable energy sources for years. So why the sudden pivot? The answer lies in the difference between intermittent power and firm power. Wind and solar are intermittent, meaning they're weather-dependent. If the sun isn't shining or the wind isn't blowing, power drops, unless you have massive, incredibly expensive battery storage on standby. But AI workloads are relentless. They require reliable, constant electricity. A data center absolutely cannot afford a drop in voltage. They require what energy experts call firm power. Reliable 24/7 base load capacity that ensures absolute grid stability every single hour of the day. Which leads perfectly into Section 4, the nuclear conversation. This desperate need for 24/7 low-carbon, firm power is exactly why the industry has aggressively shifted toward nuclear energy. Now, while traditional nuclear plants are massive, multi-decade projects, the tech industry is heavily focused on SMRs, or small modular reactors. What's fascinating about SMRs is that they're designed to have a much smaller physical footprint, allowing them to be built closer to the actual grid demand centers. Instead of custom building every piece on site, they're designed for faster, factory-style manufacturing. Plus, a lot of these advanced designs use non-traditional coolants, things like liquid metals, molten salts, or gases, which offer some potential safety and efficiency benefits over traditional water-cooled systems. Let's map out the actual timeline of how major tech companies are trying to secure this firm power a decade in advance. In Pennsylvania, Constellation Energy is targeting 2028 to restart Unit 1 at 3 Mile Island, now renamed the Crane Clean Energy Center, specifically to support Microsoft's AI power needs. Google has partnered with Kairos Power, targeting their first advanced SMR by 2030, with a goal of bringing 500 megawatts of 24/7 power online. And Amazon has invested in X Energy, aiming for a massive, large-scale SMR deployment by 2039. The tech giants are essentially acting as the financial catalysts for the next generation of the nuclear industry. But let's look at the hurdles in Section 5. The physical bottlenecks, because as exciting as all these announcements are, nuclear energy is absolutely not a magical instant fix for AI's power problem. The bottlenecks here are incredibly severe. First, the regulatory licensing process is famously lengthy and complex. Second, while the concept of SMRs is brilliant, the supply chains for commercial, factory-style manufacturing of these advanced reactors are largely untested at scale. Then there's the intense upfront capital required, the ongoing challenge of radioactive waste management, and massive delays just to connect new power sources to the existing grid. And finally, there's the human element. The Department of Energy estimates that reaching 200 gigawatts of advanced nuclear capacity by 2050 will require an additional 375,000 workers. Section 6. The Future Energy Portfolio. Because of these massive hurdles, powering the future of artificial intelligence will absolutely not rely on a single silver bullet. Instead, experts are looking at a combined AI energy portfolio. Step 1 is maximizing efficiency right at the hardware level. Data centers are deploying novel direct-to-chip liquid cooling solutions, and companies like Amazon are already reporting a power usage effectiveness of 1.15, meaning highly efficient facilities. Step 2 is continuing to deploy massive amounts of intermittent renewables, like wind and solar, paired with advanced battery storage. And Step 3, acting as the absolute backbone of all this, is the integration of firm, low-carbon power, whether that's nuclear, geothermal, or other consistent energy sources, to keep the grid perfectly stable. So the ultimate takeaway from this explainer is a fundamental shift in how we need to view digital technology. The cloud is not ethereal. Artificial intelligence does not only run on code. It runs on thousands of miles of copper wire, heavy concrete, vast cooling systems, and massive electrical grids. It is a deeply physical, deeply industrial undertaking. As AI models grow from billions to literally trillions of parameters, their thirst for electricity will only deepen. The future of AI won't just be decided by researchers tweaking algorithms inside a digital model. It's going to be decided by urban planners, utility regulators, and energy engineers. The real question we are left with is this: as we race toward artificial general intelligence, are we truly prepared to build the massive physical systems required to keep the lights on?